I'll be presenting on the use of density-based spatial clustering of application with noise, DBSCAN clustering for record linkage in observational HIV cohort. My name is Victor Olago, the data manager, National Cancer Registry. So I'll start by giving a little bit of background to this study. So the South African HIV cancer match study, SAM study, is a probabilistic record linkage study. It involves creation of an HIV cohort from HIV test records from the National Health Laboratory Service. This cohort is then linked to the pathology-based South African National Cancer Registry dataset. So this linkage aids in establishing cancer incidence among HIV positive population in South Africa. At present, the SAM study dataset includes 51 million HIV-related laboratory test records from 2004 to 2014. The current deduplication techniques cannot cope with this massive data, considering the hardware that we have at our disposal. So this prompts for more effective ways of deduplicating this big data. In this work, we explore the power of machine learning by applying clustering techniques to perform data deduplication. So our aim was to use density-based spatial clustering of application with noise to perform big data deduplication. So we used HIV test records collected in NHLS corporate data warehouse for the period of 2004 to 2014. So the deduplication process involved data preprocessing, deterministic deduplication, and word analyzer using biograms, and then transformation using TF-ID vectorizer, and then clustering with using DBSCAN, and then we assign cluster labels to records that potentially belongs to the same person. So this is a graphical representation of the whole process, whereby we retrieve the data from the NHLS CDW, and then we perform the cleaning and standardization in order to maximize on the deduplication process, and then we run it through deterministic deduplication, and then this is the whole process of DBSCAN clustering. I'll come to this in a bit, but after that we assign cluster ID, whereby we overwrite the deterministic ID in case records form a cluster, but we retain a deterministic ID in case a record didn't belong to any cluster, and then we evaluate the linkage quality using records with ID numbers. So the bigram word analyzer generates section of 2 character per demographic string. So an example would be if I use my name Victor and I want to generate biograms. The result would be VI, IC, CT, TO, and OR. So we did this for all the demographic characters that we used for this linkage, for this deduplication. And then we ran this through a TF-IDF vectorizer. So this converts the raw document into a matrix of features. So it now converts it into numbers that a machine learning model can use. But being that we're using TF-IDF, it weights the string according to how important this section of string or biogram is to the whole corpus. So DBSCAN is just unsupervised machine learning algorithm that separates clusters of high density from clusters of low density. Clusters of high density, and the clusters of high density will be assigned a cluster ID. The ones for low density will be treated as noise. So, but there are two important parameters that you have to work with in a DBSCAN algorithm. One of them is epsilon, and then the other one is the minimum points. So epsilon specifies the distance between two data points for them to be considered a cluster, while the minimum points that's the number of points that exist between the set epsilon range for them to be considered a cluster. So in our case, we used an epsilon of 0.5, and then if two or more data points fall between 0.5 and below, then they would be assigned a cluster ID. So this model starts from arbitrary point, then retrieves the neighborhood information, and then form a cluster if the epsilon is within the specified number, and there are two or more data points. So after that, after we ran this whole process, we evaluated the performance of our clustering technique using records with ID numbers. So the records with ID numbers acted as our ground truth, and we calculate precision, recall, and F measure. So precision is the ratio of correctly predicted positive observation to the total number of predicted positive observation. So precision could be true positive over true positive plus false positive. And then recall is the ratio of correctly predicted positive observation to the actual class. So recall would be true positive over true positive plus false negative. F measure is the harmonic mean between precision and recall. So harmonic mean it's just measuring how is the model performing overall. We had a total of 51 million records. The deterministic duplication resulted into 20 million. It's still a big data. And then DBSCAN clustering resulted into 14 million. So assessing the duplication quality using records with ID numbers, we achieve a precision of 0.96, a recall of 0.94, and an F measure of 0.95. Our study demonstrated that DBSCAN clustering is an effective way of deduplicating big data set in resource-limited settings, like the settings we are in South Africa. This enabled the refining of HIV observational dataset by accurately linking test records that potentially belongs to the same person. This methodology creates opportunity for easy data profiling to inform public health decision. I would like to acknowledge the funders of this project. and thank you.